All right, thank you. It's a long way to the front here. Hopefully you can all hear me okay. I can hear myself, so that sounds probably good. My name is Vicky Levy, and I'm a PhD student at the Open University. So it's my project work that I'm going to be talking about to you today. So if you could give me an 8-minute shout somewhere, that would be brilliant. Thank you so much. Okay. So what I'm going to do is I'm going to start off by giving you a bit of an overview of the concepts behind the project and the aims that we intend to achieve, and then a bit of an update on the work we've done so far and the future steps. So the overarching concept for this work was the development of a tool to assist with in-situ resource utilization, or ISRU for short, on the lunar surface, whilst also using this opportunity of having access to lunar material in situ to do some scientific work as well. So I think probably most people will have been at the morning sessions, which kind of explained really well what ISRU was, but just in case you weren't, or in case you missed it, by having a wee nap through that one. ISRU is basically making use of the resources which are close at hand. So on the lunar surface, we hope that by doing this, we can reduce mission costs and also enable a more sustainable means of exploration. On the lunar surface itself, the resources we're targeting are, of course, the regolith as a building material and anything useful that we can extract from the regolith. So we're talking about useful metals, oxygen, water, anything which could be used in situ to assist with our mission planning. So this project, the development of that tool, the tool that we opted for was a miniature magnetic sector mass spectrometer, which is a little bit of a mouthful. And basically there are 3 aims that we want this mini mass spec to be able to achieve. Starting off our ISRU aim. So we're looking at enabling in situ resource evaluation. And the reason that that's really important for early stage ISRU is we really want to know what is up there on the lunar surface and how much of everything there is. If we can figure out the abundance and the distribution, that really tells us how useful that is as a resource and how we're going to be able to actually harness that. So the resource we're going to target, we're looking at lunar volatiles and in particular lunar water, because that's going to be really useful in these very, very early days of ISRU for lots of different reasons. We're going to do this in the lab by heating up icy simulant samples that have been prepared under stepwise heating and releasing water from them. And then we should be able to analyze the water that comes off that. So we can tell what type of water that is and also the abundance. So if you did this in situ, we'd be able to get a much better idea of the spread of water across the lunar surface and just how much heating we need to put in to get that water out as well. Second goal is our science goal. So there's lots of great volatile science that you could do on the lunar surface. And unfortunately, the parallel sessions at the minute are about lunar volatiles. But learning more about the volatiles, again, it helps us to understand the distribution in terms of them as a resource. But scientifically, what we're interested in is the origin and the evolution of these volatiles and how they move from one place to another on the lunar surface. As we're developing a magnetic sector mass spectrometer for this project rather than another type of mass spec, that also unlocks some of the science which needs a higher resolution. So that means we can also do things like isotopic analysis with this. And this project, again, we're working with IC prepared simulant samples in the lab, but we're aiming to be able to analyze the deuterium-hydrogen ratio of these samples. And the reason that that's important is you can look at the DH ratio of a sample and compare it to the DH ratio of other water samples from elsewhere on the lunar surface, elsewhere across the solar system. And it gives us an insight into where that water might have originated. There's a lot of great work that's going on and in that field at the moment in terms of analyzing return samples, analyzing meteorite samples, but what we don't have is any in situ analysis. So it would be hoped that a tool like this in situ could be widely deployed all over the lunar surface, and we just add so many more data points to our current understanding of lunar water and its origin. Last but not least then, a miniature magnetic sector mass spectrometer would be much more widely useful than just the science and just the ISRU objectives that we've identified. It would also be more widely useful in terms of process monitoring on the lunar surface, so ISRU and ISRU adjacent activities, things like having a look at the air quality in habitats, for example, leak detection or studying the exhaust gases that come off some of these ISRU processes. Having a small scale device like this that could be easily deployed on the lunar surface would be really good also in that respect. So being able to kind of prove that we could do these three things, that's the overall aims of our project. So to achieve this then, we're miniaturizing the magnetic sector mass spectrometer, and it's going to be miniaturized to the extent where it's compatible with the CubeSat form factor. So these 10 by 10 by 10 centimeter cubes or units that are really widely used. And I've heard a couple of talks over the past couple of days about sort of miniaturized equipment and how that would integrate into larger rovers, for example, to be deployed anywhere on the lunar surface. We wanted to be able to operate in two kind of modes. So with gaseous samples, so with a gas processing system, so we could prove that we could use it for process monitoring to analyze the constituent parts of any gaseous sample that we put in. But also with our icy simulant samples, we could couple it with a miniaturized heating system to heat up those samples and get the analysis, and also potentially also combine it with a miniaturized drilling system. So it would be a complete cubesat compatible end-to-end system for volatile extraction and analysis. So this is currently set up in the lab at the Open University in the UK. So what you can see here on the slide, you can see it set up in its vacuum chamber there, just on the right-hand side. And then we've got a CAD rendering just underneath, so you can see it a little bit better. I have brought a model so you can see the scale that we're talking about. And it is literally that big. So it's teeny tiny, that's the magnetic sector part. This weighs in at about 700 grams, the real thing, not the model. And that includes the detector as well. So we are talking really small scale at the moment. We've also developed bespoke electronics and control software for the system that we're using at the moment. So we can program it to do pretty much anything that we want it to do. And it operates in two different modes. So basically what we can do is we can put a sample in, and we can either do a sort of broad scan of different masses that are within that sample, or we can set it to a kind of focus mode so we can focus on a particular mass that we're interested in within that sample and then get it to measure over a longer period of time so we get more detailed information. And as part of this project, I've done a bit of modeling work. So this is using a piece of software called Symposium. And basically what it does is it shows you the path of the ions as they travel through the mass spectrometer. We've got a permanent magnet as the magnet that we're using as part of the mass spec. And basically what you do is you vary the voltage that's coming in, and then that varies the mass that passes over the detector. So this here, it's just some of the common things you might find in air. I picked those because they're quite nice and easy. And you could just see it varying the voltage and the detector is quite small to spot, as you can see there, but it is in the middle, and they just pass over that. So you can either choose what you want, or you can have this broad range scan. And we intend to have two detectors, so one for each of those modes by the time we have completed the next stages. So in terms of what we've done to date, thank you. We've started our kind of preliminary testing to get preliminary results as to what it can actually do. It works, which is the good news. At the minute, we've got a resolution of about 8, which is for this stage is pretty good. It enables us to do our DH ratio analysis. And we're hoping to improve that to at least a ratio of 16, 17, so we can do our water analysis as well. These are just really early stage plots, just using the lab air. But at the minute, we're going to be putting gases, hydrogen gas, and trying to get our first results from our deuterium hydrogen testing as well. Mass range still to be determined, but we know it goes down as low as hydrogen, and we haven't explored the full voltage range yet, but it goes up at least up to 44, which includes many of the useful species for our process monitoring. So last but not least, the next steps. We really need to make sure we can get the best results possible. So there's going to be a lot of work in improving, reducing noise on our system before we start probably working with our kind of science data. We need to get set up a heating system so we can work with our solid icy samples in the lab. And then we will try and integrate that as much as possible into having something towards this end-to-end system as far as our kind of time allows. So we would eventually want to have the full extraction, heating, analysis, end-to-end project that we could demonstrate. And last but not least, we're talking about the moon here. This is ELS, but this is something which is also applicable to Mars, to asteroids. It's much more of a general tool to assist with surface operations. And that is the end of it.